Hey, today I'm going to be talking about proportionalities. So, A is proportional to B if it is the case that when one of either A or B is equal to 0, that the other is then equal to 0 as well, as a result. And it is also the case that changing one of those parameters by some factor changes the other parameter by that same factor. So those two properties are implied by the relation A is equal to KB. If A is proportional to B, that is the relation that is implied. And you can do some math, you can figure out that this equation can be used. So if you have some case where A1 is related to B1, so those are some distinct value of A caused by some value of B, or some distinct value of B caused by there being some set value of A. Sort of like a coordinate point, as well as these two values of A and B. Well, you can divide that out and you get the ratio of B's across the two situations, and the ratio of the A's are equal. So if you know those across in one situation, and you know one of these in another situation, you can find the other. So here's some simple examples of where you can use these proportionalities to come up with an equation that pretty well describes what's going on. So one example is food consumption. So we're going to compare all the things sort of separately and consider holding other variables constant while we compare one thing that changes. So let's say food consumption is proportional to the number of people. So doubling the number of people in a society doubles the amount of food that needs to be consumed. So we can say if time is held constant and food consumed per person per unit time stays approximately, or on average stays constant, then you can say food consumption is proportional to the number of people. You can also say food consumption is proportional to time in the conditions that the number of people is held constant and the food consumed per person per unit time is held constant. So you can see that even though if we're considering those other variables to be constant, they're still involved in the expression. They still, whatever that value is still makes a difference. And we could vary both those things at the same time, and both their effects would come about multiplicatively in the effect on the food consumption. So what that means is you can come up with a formula from this that says mass of food consumed is about equal to the mass consumption of food per person per unit time multiplied by the number of people multiplied by the time period over which you're considering this. And this is for dimensional analysis, and you can treat the dimensions of each thing sort of like prime factors. So like you have mass over person times time, then you multiply that person time by person times time, and you return mass. And that's what you want on this side. You want it to evaluate to give you a dimension of mass, because that's what's on the left-hand side. You can do a similar thing for uniform motion. So distance is proportional to time in the case where velocity is maintained. You could also say distance is proportional to velocity in the case where time is held constant. So if you're looking at two different situations occurring over similar time ranges, so same time range, if you double the velocity in one situation over which at which you're running for that time, then you double the displacement, the distance over which you run. So next, you can make a dimension and a unit in that dimension for anything that is quantitative. And if you can say something's proportional to another thing, you're sort of thinking about it quantitatively already, so it shouldn't be too hard to give it a unit and a dimension to which you measure that. So like for number of people, for example, the unit in that dimension would be one person. Multiply that by the number of people, you get some dimensionless number. Alright, thanks for watching.